Good day everyone. So for today I'm going to discuss gas absorption and stripping. This particular lecture discussion is divided into two portions. So the first part will tackle on the basics of gas absorption and stripping, the material balances, and the other needed principles in determining limiting flows. The second part, which I will discuss on our next meeting, will cover the design of the columns or the equipment themselves. So when we speak of gas absorption, it's a unit operation in which a soluble component or soluble components of a gas mixture is dissolved or are dissolved in a given liquid solvent. Now, the inverse of gas absorption is stripping or desorption. It is the inverse because this time the component that is to be transferred is from the liquid and the solvent this time is in the form of a gas. Now, both this absorption and stripping has something in common with distillation because they need special equipment that needs to provide the contacting of the two phases. That way mass transfer will occur. Now, having mentioned the two phases, so for gas absorption and stripping, there are two phases, the gas phase and the liquid phase. In the case of gas absorption, the solvent is the liquid phase. In the case of stripping, the solvent is the gas phase. Now, absorption, stripping, and distillation operations are usually carried out in tall, vertical, cylindrical columns or towers. And in these towers, we may have either structured or unstructured or random packing materials. This we will discuss when we go to the design part of the columns. Now, the phases here normally contact each other counter-currently. So, they have opposite direction, but all with the purpose of providing or making, or shall we say establishing, a bulk phase where a particular interface can be made where the actual mass transfer occur. So the two phases will mix, they will form the bulk phase, and in the bulk phase we will have the formation of the interface. This is where specifically the mass transfer will happen. Now, if you recall in our discussion with phase equilibria, we have discussed laws that will express relationship between the mole fractions XA and YA for a particular system. So, in this case, we will also be using again these laws. So, Henry's law is one law, and then the other one is Raoult's law. The difference between the two as a review is that Raoult's law is only applicable for ideal systems, whereas Henry's law can work for both ideal and non-ideal systems. So since these are equations that are not any more new to you, I will just simply pass through this and proceed with something that is new. Now, in your handbook, there's a formula that allows you to determine the solubility of a gas in the solvent water. So, if the solvent is not anymore water, we cannot make use of the formula that is placed in the slide. So, the formula will only need one variable, and that is the mole fraction of A, referring to the gas, in your liquid. Now, the MA, or the M sub A specifically, and the M sub W are molecular weights of the gas and the water respectively. So we only have one variable, and that is the molecular, or rather it's only the mole fraction of A in the liquid phase. Now, we have this sample problem in terms of the use of Henry's law and the concept of solubility. Now, in here, you are asked to determine the solubility of carbon dioxide dissolved in water at 293.2 Kelvin when the solution is in equilibrium with air at 1 atmosphere pressure. Now, Henry's law constant is given already with a value of 1.42 times 10 raised to 3 atmosphere per mole fraction. Now, moreover, the mole fraction of carbon dioxide in the gas phase is 0.43. So take note that the problem is talking about the mole fraction of CO2 in the gas phase, which is 0.43, but it is asking for the solubility of CO2 dissolved in water. So, if it's the solubility of CO2 dissolved in water, then this must be a problem which is just an application of this formula that was discussed just a little while ago. So then, we have to look into the choices that were provided. So if it's solubility of a gas in water, our answer must be in the form of mole fraction, as expected, because the given here is mole fraction also of CO2 in the gas phase. But if you look closely on the choices provided, they are not mole fractions, but rather they are in parts per million, or milligrams per liter, which is just an equivalent of the parts per million. So let's see on how we're going to solve this particular problem, come up with the solution with the choices that are provided to you. But nonetheless, we know for now that the answer to this problem is 736 parts per million, meaning the solubility of CO2 in water, given that its mole fraction in the gas phase is 0.43, is equal to 736 parts per million. So the question is, how do we get this value of 736 parts per million? So let's move on. Now, if we recall Henry's law allows you to associate partial pressure of A with the mole fraction of A in the liquid phase. Now, what we did on the original Henry's law equation is divide it by the total pressure of the system to come up with an equation that relates the concentration of A in the liquid phase to the concentration of A in the gas phase. And since the problem gives the value of the mole fraction of CO2 in the gas phase to be 0.43, we substitute it in the formula here. And this one is already your Henry's constant. Your Henry's constant, which we have divided by the total pressure of the system. So if you look back to the problem, it says that your Henry's law constant is 1.42 times 10 raised to 3 atm per mole fraction. Now if we go back here, so it's 1.42 times 10 raised to 3 xa as well. So notice that I did not have any effect or change. The equation did not have any change on the constant, the Henry's law constant. It's because the unit of the constant and the total pressure of the system are the same, and thus they are in both atmospheres. So there's no need for us to convert. In this case, your original Henry's law constant was just simply divided by 1 atm because that's the total pressure of the system. So from Henry's law equation, we have already the value of the XA. Actually, this is already the answer to the problem. If the choices were only provided in such a manner that the unit or units would be the same as the one that we got here, as I have mentioned a while ago. So there's a need for us to convert our answer into an expression that is equivalent to the units that appears in the choices. So since the choices are all in parts per million, we have to convert our set of units here of mole fraction into parts per million. Now, how do we do that? So first, we need to determine the mole ratio. Mole ratio meaning the ratio of CO2, moles of CO2 to moles of water in our system here based on this particular mole fraction. So this one implies that for a total number of moles of 1 for CO2 and water, your mole CO2 is only 3.01 times 10 raised to negative 4. Which by algebra will tell you that the moles of water would be then 1 minus this particular value. And that would give us a 0.999699. So I am converting now the mole fraction into mole ratio. So look at the unit specifically. The numerator is mole CO2. The denominator is mole water. So it's not mole fraction anymore, but rather mole ratio. So I have now mole ratio. Why convert into mole ratio? Because I want to convert the moles here into mass units. We know for one that when we speak of parts or parts per million or parts per billion, the units that is equivalent to are in mass units. So there's a need for us to convert the mole units here into mass. So simply, we will use the molecular weights of CO2 and water in that sense so that we will be able to convert from mole CO2 per mole water to gram CO2 to gram water. Now you see very closely, the answer is now gram CO2 grams water. If I want to convert it into parts per million, meaning the denominator should be 1 million. So if I will move this one to the right, that would be 1, 2, 3, 4, 5, 6. This would be 736 times 10 raised to negative 6 grams CO2 per gram water. So, since this is per gram water and I have here a 10 raised to negative 6, it's just like saying that this is grams CO2 per 1 million grams water. So, if it's per 1 million grams water, then that would be then 736 parts per million for the degree of solubility of CO2 to water. So, a very simple formula was used, but the manner in which the problem is phrased allows you to recall other concepts learned in your basic chemistry classes as to how we're going to convert from mole fraction to parts per million. And this particular problem is a board problem, by the way. So this is how that's how you're going to solve, applying that particular formula that is found in your handbook. Now we go to the next topic here, which is on equipment selection. So packed columns usually are chosen for very corrosive materials, for liquids that foam badly, or for either small or large diameter towers involving very low allowable pressure drops, or for small-scale operations requiring diameters of less than 0.6 meters or around 2 feet. So whether we have to choose between a tray absorption tower or stripping tower to a packed absorption tower, the packed column has this advantage over the tray column. Now, plate columns may be economically preferable for large-scale operations and are needed when liquid rates are so slow that packing would be inadequately wetted. So, if the velocity of the liquid in our packed column will not be sufficient to ensure that all the packings inside the column, whether random or structured packing material, are adequately wetted to ensure that there is the formation of the interface, then the plate column is advised to be used over the packed column. Now, plate towers may have a better turn-down ratio and are less subject to fouling by solids than packed towers. So, fouling meaning the deterioration of anything inside the column caused by the long presence of solids encrusted in your packing material. So, they get fouled up if they are not removed from the packing material. So, the plate tower, if I may say, will be a lot cleaner in terms of how it's operated than the packed column because there's no worry about this fouling. Now, as for the turn-down ratio, it's the ratio of how much you are producing or removing from the column in terms of what's being admitted or what is being processed by the column. So, it's actually the output over what's processed by the equipment generally when we speak of the turn-down ratio. Now, for the gas absorption diagram, this orientation is based on Giancouplis orientation. So, the number of stages or the number of plates is numbered based on the entry of the solvent. So, since in gas absorption, the liquid phase is the solvent, for whatever or wherever it enters the column, that should be the first stage. Since our solvent enters this stage here, then this would be level 1 or tray 1. And of course, the last one will be tray N. Now, the phases, this V1, this V sub N plus 1, this L1, and this LO are having subscript based on the stage or the plate in which they came from. Now, since this particular liquid phase, our solvent, is entering plate 1, then or stage 1, then we are to view that it came from stage 0. As such, we label it with L sub O. Now, in here, this particular gas phase, V1, came from stage 1 because it's the arrow here is coming from stage 1. So, it's labeled with V1. This liquid phase is coming from tray N or stage N, so it has a subscript of N. This particular vapor that is to be separated or processed is entering stage N, so it is of course to be understood that it came from stage N plus 1. This is how we number stages or phases in Giancouplis orientation. But in terms of McCabe and what you have in your handbook, we label the column, the absorption column, as these phases here have subscript 1 and the phases here on top have subscript 2. Again, the phases here is subscript 1 and in here it's 2. That's in terms of McCabe numbering. Now, in terms of stripping, we also follow the same principle as what we have in gas absorption. This is also naming based on Giancouplis orientation. So, if this is the solvent, because this time the gas is the solvent, then this must be tray 1. And this must be tray N. And the number or the letter that appears or the number that appears in the subscript of our phases as labeled is based upon the tray or the stage in which this particular phase came from. So this was coming from nth stage or n tray. So that's such we label it as V sub N. Okay? So this orientation is again based on Giancouplis. So if it's McCabe, it's always 1 here and it's 2 here. So we start at the bottom and we end on top. Now, in terms of types of towers and columns which facilitate gas absorption or stripping, they could either be in the form of tray towers that was shown to you a while ago. It could be in the form of pack towers. It could be in the form of straight spray tower wherein the liquid is being sprayed downwards against the vapor that is flowing upward. As such, the name spray. So, liquid is sprayed downwards against or countercurrent a vapor that goes upward. The bubble column is the opposite of this. The gas is bubbled up against a liquid solvent that is going down. So, notice that in all this scenario, the vapor is introduced at the bottom, the liquid is introduced on top. This centrifugal contactor is not so common and its application is very specialized depending on the type of separation and the system that is to be processed. But nonetheless, aside from the contacting, so vapor is still being introduced on below and liquid is being introduced on top, we have the presence of an additional force, and that is the centrifugal force that will enhance the separation of the desired component from the gas, transferring it to the liquid solvent by virtue of what we call as the centrifugal force. But in terms of where the phases are introduced in these 5 equipments, they are all the same in the same manner introduced. Vapor at the bottom, liquid on top of the equipment. Now, when we do material balance for a single stage system, so if this is stage 1, it's a single stage system, so this is stage 1, the way we label it based on John Couples is of course this one. LO, L1, V2, V1. The living phases, L1 and V1, are labeled based on the stage that they came from. So that's 1. Whereas the phases that enters the single stage contactor are labeled also based on the stage where they came from. So this must be coming from 0 stage because it's entering stage 1. This must be coming from stage 2 because it's entering stage 1. So again, same principle applies. Now, if we do our material balance for this, so we add the entering streams, we equate it to the sum of the streams that leave the contactor. So this would be our equation for that. LO plus V2 is equal to L1 plus V1. These two, the sum of these two phases is what we call as the bulk phase M. When we do component balance, either in terms of A, the component that is being transferred, or in terms of another component C, it's just patterned after what you are seeing on the total mass balance equation. So you multiply the L's with the mole fraction in the liquid phase X, and you multiply the V's with the mole fraction in the gas phase, which are the Y. So we label them as, in this case, XAO. The O here because it's, of course, paired, or it's the mole fraction of the liquid that enters the column, your solvent, so XAO. The numbers that appear are all the same when we pair them up. I'm referring to the stream and the concentration in which it is being multiplied to. Now, as to the concentration representation that appears in the bulk phase M, it's represented as X. Okay? Just like the liquid phases, which are also having concentrations represented by X. In our system, whether binomial or not, the sum of the mole fractions of the components in the gas or liquid phases are all, at all times, equal to 1. Now, there's another alternative formula that we can use if, in this case, a simple total mass balance equation and a component balance on a particular component will not solve the problem for us. And actually, most of the time, this particular equation works. This equation uses the inert parts of the streams. When we speak of inerts, for example, if your solvent stream or your liquid phase has a little of the solvent as it enters the column, that part which is not has a little of the solute rather as it enters the column, that part which does not contain the solute is your inert part. Most of the time, our solvent is water, so it's to be viewed as 100% inert, and there's no XAO because we don't have the solute present on it. Now, it's the same thing with the gas. With the gas, we also have the inert part of the gas, which is oftentimes is air. So let's say CO2 air mixture, the part which is air is your inert part, or that's your V prime. So take note that the moles of inert streams are being multiplied not to mole fractions but rather to mole ratios. Actually, this expression is already mole ratio of A. The smaller excess here is mole fraction of A. So we converted from mole fractions to mole ratio. And we are using mole ratios all throughout in this particular equation, in which we're using the inert parts of the streams. These are the streams entering, and these are the streams leaving our particular equipment. Now, to illustrate the use of the material balance equation, we have this sample problem of a gas mixture having a total pressure of 2.026 times 10 raised to 5 Pascal. Now, this gas mixture, take note, is composed of air and SO2, and they are contacted in a single stage equilibrium mixture with the solvent, which is pure water at 293 Kelvin. Pure water meaning your water does not contain SO2. Now, the partial pressure of SO2 in the original gas that enters the column is 152 times 10 raised to 4 Pascal. The inlet gas contained 5.70 total kilogram mole and the inlet water 2.20 total kilogram mole. Now, take note of this italicized sentence. The exit gas and liquid leaving are in equilibrium. Now, in every stage, whether it's a single-stage system or a multi-stage system, the exiting phases or the phases that leaves a particular state are always said to be in equilibrium. If they are in equilibrium, the equilibrium equations or formulas like Henry's law and Raoult's law are applicable in terms of expressing the relationships of the concentration of the liquid phase and the gas phase that leaves a particular stage. So again, the equilibrium equation is only applicable for phases that are equilibrated. So in this case, we are using it on phases that leaves a particular stage or a single stage unit. Now for our problem, we are to calculate the amounts and composition of the outlet phases. The amounts and their composition, and we are to use the data from figure 10.2-1. This problem is patterned from Giancouplis, and this equilibrium data from figure 10.2-1 is simply the linearized relationship between XA and YA by Henry's law. And this is the linearized curve. So this is the original curve. Henry's law linearizes it in the form of this line. So partial pressure now is having a linear relationship with mole fraction in the liquid phase. For in this system that is given as an example for SO2 water system. So take note that since we're using it in the problem, this will be the Henry's constant that we're going to use. And take note, the unit of the partial pressure, it's atmosphere. So we are to be very careful with the unit of Henry's constant because some problems are not giving pressure units in atmosphere. And we may wonder why we did everything correctly but our answer is still wrong. It's because our units don't agree. So if we will go back to our problem, okay, this is our problem. This is how it's supposed to be solved. So I have the illustration here for a single contacting stage. I have the material balance equations here. Okay, as you can see. And this is the alternative equation that I can use just in case these two will not work. From equation 1, I will add the values of the streams. This is for the solvent, yes, water. And this is for the gas mixture, which is 5.70. We do not know the L1 and the V1 because it's being asked by the problem. So the sum of these two is 7.9. Now, if you use the second equation, so we substitute the values. It's pure water for the solvent, so XAO is 0. And we have this for our gas, YA2. And we have this 5.70 for the V2. And we still do not know any of this. So we have 1, 2, 3, 4. 4 unknowns here. And 2 of the unknowns here appear also on our first equation. So as it is, by the rules of algebra, we cannot process this problem just simply limited to these two equations because we cannot solve for what we're looking for. But nonetheless, before I proceed on how we're supposed to attack the problem, because we have two equations with 4 unknowns, I will explain why you have this for the 0.0750. Okay? So the problem says that your partial pressure for SO2 in the original gas is 1.52 times 10 raised to 4. And the total pressure is this. So from Chem 1, if you want to determine the mole fraction of A in the gas phase, simply divide its partial pressure by the total pressure of the system. So that would give you this value, which is 0.0750. Now, so going back to what I'm saying, we cannot make use of this for now. Probably we can use this, but this one, this equation 2 cannot help us solve the unknowns. So we need to use some alternative, and the alternative, is this one. We need to determine the inert amounts of the stream. So inert amount for water is still the water itself because XAO is 0. The inert part of the air and the gas is the total value that enters times 1 minus YA2. And that should give us a value of 5.2725. Where is this coming from? That's your 5.70 times the quantity 1 minus 0.0750. That should give you this one. So now in terms of this equation, I have already something to substitute to the L prime and the V prime. XAO is already 0. YA2, what is this YA2? That's the mole fraction of the gas that enters the contacting equipment, or the mole fraction of A in the gas mixture, and that's 0.070. So now we have everything there. So you will go to the next slide. So it's explained here as to YA2, and we have this one here. Now if we substitute the mole fraction and this one, the mole of air, if you take out 0.050 from 1, so that would be 0.925. This is XA1 and this is also XA1. In the original formula class, if I may go back, this is YA1 and this is XA1. There is a need for us to express YA1 in terms of XA1, and we have done that by using Henry's law. So using Henry's law, since XA1 and YA1 are mole fractions of the phases that leaves our column, then it is said to be, they are said to be in equilibrium. If they are in equilibrium, then Henry's law is applicable. So you have this and this. Now I will replace the YA1 here in terms of this equation. Simplified. So notice again the conversion. I have mentioned already that there's a need for us to convert. So we converted the total pressure in Pascal to atmosphere because our Henry's constant is in atmosphere. Then this YA1 will be substituted here. The XA1 is intact. We have these values already solved in the previous slide. And now we get to know the value of XA1 and the corresponding YA1. Where is this taken? From here. You substitute XA1 here, you'll get YA1. Actually, since this equation will yield a quadratic equation, there are two sets of values you'll be getting. This is one pair, which I have highlighted in yellow, and this is another pair of values. But this one I highlighted in green because there's no mole fraction that is more than 1 in value. So what we did, we only use the value that is acceptable. So there has to be some validation on the values that we're getting. So we use these two values because they are acceptable. Now, moving on, I have already the concentration of the liquid and the gas phases as they leave the column. Then we need to find the amounts because we are asked to find the amount. From equation 1, since the total number of moles of the 2, LO, and V2 is 7.9, we can express V1 in terms of L1. Now, this we will substitute to equation 2 in lieu of V1. This equation 1 and equation 2, by the way, are these two. Okay? Are these two. Now, if we substitute the values that we have for XA1, YA1, and V1 in terms of L1 here, we will get these two values for the streams. So, we have solved already the problem. We have answered the values of the exiting streams or the phases that leaves the column, and we have answered the mole fraction. So these are the mole fraction in terms of A. If we want B, we only need to subtract these two values from 1, since we only have a two-component system. So our XB1 and YB1 are these two. So we have solved our problem already based on the application of the material balance equation and the component balance equation. Okay? Now, actually, in principle, we use the same concept or logic in handling multi-stage processes. The only difference of the multi-stage processes with the single-stage process is because you have already a series of stages here to consider. But the labeling in principle is still here based on Giancouplis. You still have LO entering stage 1. You have V1 leaving stage 1. You have LN, this is the last stage, leaving stage N of our column. And we have V sub N plus 1 as the amount of gas that is to be processed by your column because it's still entering stage N. Now, we use material balance here, same as the single stage unit, differently labeled. We also use the same principle for coming up with the overall component balance. And this is it. And this is how a column looks like if it's a tray tower. So you have LO, you have V1, you have Vn plus 1, you have Ln. Okay, here you have a tray absorption tower. Now, if it's a pack tower, so you have packing material in between, you have V2, L2, V1, L1. Notice I used this particular illustration because this time you're using ones for all the streams below the column and we're using 2 for all the streams on top of the column. If you want to use the orientation of Giancouplis, it's fine. If you're going to use the orientation of McCabe, it's fine. But don't get confused because even Giancouplis also used the two form of representation, his and McCabe's, interchangeably. Meaning at times his formula is based on McCabe's orientation, at times his formula is based on his own orientation or representation of the streams that enters and leaves a column. If in the single stage contactor or equilibrium system for gas absorption, we have an equation that uses inert phases. These two are already used. Then we can also use that particular equation here. If you notice, I have L primes and V primes, L primes and V primes. And as such, the need to just simply represent the faces that are at the bottom of the column by 1 and the faces that are on top of the column by 2. So this would be your alternative equation. The equation that I am labeling here is based on the current edition of the handbook. So equation 14-12. So please check. If your edition does not come up with this equation, then probably it's the other edition, the older one. Now, when we place in our operating lines for the processes gas absorption and stripping against the equilibrium curve, representing the relationship X and Y for our system, we know in part if we're doing it right if our operating line for gas absorption is written on top of the equilibrium curve, while that of stripping is written below the equilibrium curve or the equilibrium line. Take note again, this is a graph expressing relationship of X and Y. Now, as to what will help us plot, although you don't need to plot now because everything is analytically to be solved, what will you need in order for you to plot the operating line? You need only the concentration pairs. Y2, X2, this is on top of the column. This is Y1, X1, this is at the bottom of the column. For stripping, this is the tower bottom, Y1, and for the top of the column, Y2. Okay? Tower bottom, tower top of the column. Now, before we will know how to determine the number of stages that will allow us to, in terms of objective, shall we say, realize our objective of recovery. Let's say we want to have a 99% recovery or a 95% recovery. We have to design our column in such a way that it should contain the accurate or the approximate number of stages for contacting. If not, our desired recovery won't be realized. Now, what is this equation that allows us to determine the number of stages or trays? So, stages for packing towers, trays for tray towers, that will help us achieve the desired recovery. So, this is the Krimser equation. Equation 14-33 of your handbook. In here, you will be needing the gas absorption factor A, and you will be needing the mole fractions of the gas phases and the mole fraction of the solvent. Now, if your gas absorption is 1, so meaning your operating line is straight, this complicated formula that has the Ln will now be simplified into this form. Now, that is if A is a constant and having a value of 1, then it will be a simple formula as this. If A is a constant but still does not have a value equal to 1, you will have to use this one. Okay? So, A is the absorption factor, M is the slope of the equilibrium curve or line. This is given most of the time by the problem. And L over V is the slope of the operating line. So, the L over V ratio for the bottom of the tower and the L over V ratio for the top of the tower are two different ratios. They may not be equal in the case of operating lines that are not curved. But for operating lines that are more likely to be straight with a very little or minimal curvature, the value of these A's are more or less on the same range, or they are very much the same. Now, if the equilibrium line is curved, M and A will vary. Okay? Your slope of the equilibrium curve, of course, will vary because it's curved. And A, the absorption factor, since this one is dependent on the M, will also vary. M will be the slope of the equilibrium line on the dilute N. So, if in some scenarios, you will encounter such a problem as this, and you would be asked, what M will I use? Because my M varies, because my equilibrium curve is not a line, but a curve. Then, you will have to get the slope of the curve on the dilute N. So, M will be the slope of the equilibrium line or curve on the dilute N. The dilute end is the end of the operating line which has lesser values of X and Y. The concentrated end, since it's concentrated, so meaning the values of X and Y are higher compared to that of the dilute end. Since there's only two to compare, concentration at the bottom and on top, you just have to look which of the two is higher. If it's higher, then that's the concentrated end. If it's lower in concentration, that's the dilute end. Now, in cases wherein A will vary, you have to determine the geometric average of the two absorption factors. The absorption factor at the bottom, this one, and the absorption factor on top of your column. Getting these two separately, if they're not equal, then you get the geometric mean. If they're equal, then there's no need for you to do this because anyhow, the answer would still be the values that you have for the two. Okay. Now, for stripping, the formula for Krimser equation is very much the same, only that this time we're not using y's, but rather we're using as well x. So, you have the appearance of both the mole fractions of the liquid phases, and this one, the mole fraction of the mixture of gas that enters the column, or that is your solvent, because in stripping, your solvent is the gas. And you have here the absorption factor still. If you would be asked what is the stripping factor, it is the reciprocal or the inverse of the absorption factor. We have a case wherein A is constant and has a value of 1. This complicated Krimser formula is simplified in this form. So this would be now your new formula if A is a constant and having a value of 1. Okay? Graphically, I leave this to you to read on your books. The graphical determination of the number of stages for a gas absorption process or a stripping process requires for you the operating line. You need to plot the operating line. You need the two concentrations, the concentrated N concentration and the dilute N concentration, and you need the equilibrium line or curve. After plotting, you just have to simply make a stepwise drawing or staircase-like drawing in your operating line and in your equilibrium line in between the two. As to the number of steps that you can count, that would be approximately the number of stages that will facilitate the given recovery or separation. That's graphical. But we will limit our computations here to the analytical way of determining the number of stages and using Krimser equation. And the sample problem I'm using here is taken from John Kuplis, and it's also in the accompanying complementary file or page that goes with this discussion video. So please read on it for more or for a more detailed discussion. There are other problem samples there which are not on this slide. This is the only sample problem I took from that particular file. So they will reinforce whatever concepts we are discussing in this particular recorded discussion. Now, in this problem, it is desired to absorb 90% of the acetone in a gas containing 1 mole percent acetone in air in a countercurrent stage tower. The total inlet gas flow to the tower is 30 kg/mole per hour, and the total inlet pure water flow to be used to absorb the acetone is 90 kg/mole water per hour. The process is to operate isothermally at 300 Kelvin, and the total pressure is 101.3 kilopascal. Good that the problem specifies the equilibrium relationship of the acetone A in the gas-liquid system, and it's given by YA being equal to 2.53 XA. You are to determine the number of theoretical stages required for this separation. Before you even start solving a problem, you always have to accurately illustrate the problems. In this case, you are given YA N plus 1. This is the concentration of the gas that enters the tower. If I will go back, that's 0.01 if represented, because this 1% is 0.01. Okay, that is the concentration of the gas that is to be processed by your column. Your solvent is pure solvent, then its XAO is 0. This V sub N plus 1 is 30 kg/mole. It's given in the problem. So 30 kg/mole for total inlet gas flow. Okay, we move on. And for the solvent, it's 90 kg/mole. So pure water is to be used to absorb the acetone, and the amount of 90 kg/mole water per hour is to be used. So we have here the 4 information given in the problem. If we will account for the amount of acetone entering, that would be the amount of the mixture that enters, this 30 times the mole fraction of acetone. And this is now the amount of acetone entering your column. The entering air would be, of course, the total amount 30 minus the 0.3, and that would be 29.7, because we only have air and acetone entering our column, so you just need to get the difference of the two. The acetone leaving is the acetone that remains unrecovered. So the acetone that will leave your column will be the acetone unrecovered, and it will go with stream V1. Now here, Y1, that would be V1. So since we are recovering 90%, then the thing that left is 10%. So 10% of the amount that enter will still remain in the column because it is unrecovered. As for the acetone that is leaving, meaning it goes with the solvent water, so now it is in Ln. It is in Ln because Ln is the solvent that leaves your column. Now, this is the Xn line here. So that's your Ln. So 90% of 30 will leave your column carried by the solvent because of the 90% recovery. So take note of these values here. What you see here is just the graphical interpretation of the analytical procedure that will be discussed here. But we are more concerned with this one. Now, your V1 will be the 29.7 plus 0.03, which is equal to 29.73 kilogram mole air plus the acetone that was not recovered. So again, I will go back. The acetone that was not recovered is the acetone that leaves with V1. This acetone mixes with air because air is inert, and whatever is the amount that enters, it's the same amount that leaves the column. So that's the reason you're seeing here that V1 is the sum of the inert air plus the unrecovered acetone. So you have 29.73. If we want to know the mole fraction of acetone in this leaving V phase, the V1, that would be this acetone unrecovered divided by the total amount of air and acetone. So this is the mole fraction of acetone in the leaving V1 phase. As for Ln, it will have the water that was used as the solvent, and it will have the recovered amount of acetone, and that's the 90% of the 0.3, and that's the 0.27. So we add the two. This is already the stream that leaves the column. If we want to know the mole fraction of acetone, that would be this 0.27 recovered divided by the total amount of the solvent and acetone that leaves the column. So you already have the 0.003. Now, having known that, this will be the manner of doing it graphically. This is your equilibrium line. There has to be a table that will help you plot this line. A table expressing relationship x and y, whereas this operating line is above this equilibrium line because this is gas absorption. And the way you plot it is you use the given mole fractions. There are two mole fractions given, the 0.01 and the 0, and these two which we have determined in the previous slide. So you pair them, that way you will be coming up with the operating line for this gas absorption process. And this will be the graphical procedure. Now we go to the use of the Krimser equation because our goal is for us to know the Krimser equation. Okay, we have this value for YA1, we have this LO, we have this XAO, and we have this V1 all predetermined, and we have this YA equal to 2.53 XA as the equilibrium relationship or equation for XA and YA. Now, we will solve the value of the absorption factor in the upper part of the column, the LO part. The upper part of the column is said to be the concentrated part. So, LO over MV1. So, we just substitute the values we got. That's 1.2. We do the same for the lower part of the column. So, this time it's Ln and V sub n plus 1. This is the dilute n. So, your answer is 1.19. So, we can say from these two that more or less our operating line is straight, but nonetheless, we have to be accurate. So, since they're not equal, we need to get the geometric mean. So, your answer is 1.195. Now, if we will use the Krimser equation, substitute the Krimser equation that was discussed here. I'd like to go back to Krimser equation for gas absorption. This is our Krimser equation. If we use that, this will be the values that we'll be getting. So, we will have 5.04 stages for N. Now, if you do the graphical, if you did the graphical, more or less your answer will be 5.2. But of the two, of course, this one is more accurate. The 5.04 number of stages for a 90% recovery given the conditions that related in the problem. So again, don't assume Don't assume that your gas absorption are constant. Solve them. And whenever they're not constants, get the geometric mean. Now, the last part of the slide will have something to do with determining the minimum solvent requirement so as to come up with the optimum number of stages. For us to know the optimum number of stages, we need to know the optimum solvent requirement. The optimum solvent requirement is needed for, or the limiting or the limited or the minimum solvent requirement will be the one used in determining the optimum solvent requirement. Now, these are the orientations we have. For gas absorption, this is the operating line again. For stripping, this is the operating line again. These are our equilibrium lines, curves. For minimum solvent requirement for gas absorption, we move this line such that it would be tangential to the curve. So we move this point here until it will be tangential to the curve. For stripping, we move this point here until it will be tangential to the curve in this point. Now, in gas absorption, we are interested in finding X1 maximum. X1 maximum. For stripping, we are interested in getting Y2 maximum. Okay? How? We base it on the illustration here. But anyway, there's a sample problem that we will use in determining the minimum solvent requirement. So, a generalization based on these two this would be our guide in determining the minimum solvent requirement, whether we're talking about gas absorption or stripping. For gas absorption, the recovery X1 is at the maximum when inert solvent flow rate is minimum. So we determine X1 maximum based on the minimum amount of solvent. The inverse of that is in your stripping. Instead of L prime minimum, we use V prime minimum. The recovery Y2 is a maximum when inert solvent flow rate is minimum. It is worth noting, class, that when you solve for the V minimum, it's inert. When you solve for L minimum, it's inert because it says here inert solvent. Okay, so they are based on the inert solvent, not on the total solvent. Okay, now we will go to the last sample problem that will illustrate the use of the principles just discussed on the minimum solvent requirement. Okay, now if we want to know the optimum number of trays based on the minimum solvent requirement, this is taken from your handbook, by the way. Optimization for liquid to gas ratio in terms of the total annual cost often suggests that the molar liquid to gas ratio should be about 1.2 to 1.5 times the theoretical minimum. What is this trying to say? You first determine the minimum solvent requirement and you are going to multiply it by most 50%, 1.5, or it should be a value that is 50% more than the computed minimum if you want to know the optimum number of stages or the optimum solvent requirement. That has something to do also with this. The actual liquid to gas ratio or the solvent recirculation rate normally will be greater than the minimum by as much as 20 to 100%. This 25 rather to 100% is here. But for optimization purposes, we cannot make it 200% of the minimum because we have to realize or we have to consider the cost in optimization. So the 50% that was pegged as the maximum value here in the range of 1.2 to 1.5 is actually within the 25 to 100% more than the minimum solvent required. Okay, it's the same thing with stripping here. It's 20 to 50%. So this one is for gas absorption. So basically, they're the same. So if the problem requires to determine the optimum solvent requirement or the optimum number of trays, first go back to the minimum solvent requirement because it's needed for us to know the optimum solvent so that we will know the optimum design condition or the optimum number of trays. Okay, here's a sample problem It talks about a tray tower which is absorbing ethyl alcohol in an inert gas using pure water, again pure water, on the specified condition. The inlet gas stream flow rate is 115 and it contains 3.3 mole% alcohol. It is desired to recover 90% of the alcohol, and the equilibrium relationship is y equal to 0.78x. We are to determine the optimum number of trays. The formula to be used in determining the optimum number of trays is still Crimser equation. However, we need to first determine the minimum solvent requirement. The answer in this problem is a 4. But again, how was this 4 arrived at? So we will go through the problem. This is given. Okay, this is the given in the problem. And again, look at the way it's labeled. This is, the streams are labeled here in terms of John Copley's orientation, but I place here the orientation based by McCabe because we need it in the inert amounts of the streams later in the equation. We are, okay, para hapos, or easier. Now, if you use material balance, overall material balance, LO plus V sub N plus 1 should be equal to LN plus V1. Okay, and if you do component balance, same thing, LO XAO, and then YAN plus 1 goes with VN, LN XAN plus V1 YA1, and you have MXAM here. Component balance, and the ever very beneficial alternative for equation 2, which uses the inert phases. Okay, now from 1, we will have this. We have only one known data in 1. From 2, we have this and this. This is a 0, so this is out of the picture. And we have 4 again. Most of the time, if we use equation 1 and 2 only, we'll be ending up with an equation which has 4 unknowns. And we need to use equation 3, the alternative equation, and we need to determine the inert streams, the amount of the inert streams. In the case of water, since it's all water solvent, no solute present, so your L prime is LO. Your V prime will be your given 115, but it should be multiplied to 1 minus YAN plus 1, and that should be only 111.21. The unrecovered acetone that goes with V1 is 10% of the amount present, 115 times 0.03, and it gives us now V1, the unrecovered acetone, and the V prime which we determined here. So 111.21 plus this will give us 111.5895. Knowing V1 will allow us to solve Y1, which uses the unrecovered ethyl alcohol, and we divide by the total value of the stream, which gives us 0.0034. Now, since optimum number of trays is based on minimum solvent requirement, we solve first for minimum solvent requirement L prime based on XN maximum. We are given this relationship that YAN plus 1 is equal to 0.78 XN maximum. Where is this taken? From this particular illustration. Let me show to you in gas absorption. Okay. For gas absorption, your Y1 will be equal to M times X1 maximum. Okay? We took it from here. If it's stripping, your X2 M will be equal to Y2 maximum. In case of stripping, because we're using this line for stripping. For gas absorption, we're using this line. Okay? So, in our case, the equation you were seeing a while ago, the equilibrium relationship was based on this. The Y1 is equal to M times X1 maximum. The X1 maximum is the XN, because 1 is in the bottom of the column and it's XN in the labeling of John Copley's. And this Y1 is the YN plus 1. Okay, this is based on McCabe, the Y1 and the X1. So let's go back to our slide where we are solving the problem. So we have this already. And from here, we can determine the Xn maximum. What would be the maximum moles of ethyl alcohol that will be reflected in the solvent leaving the column if we are to use this amount of solvent? Or rather, this amount, or if we are using rather a mixture that has this particular mole fraction of the gas. Now, we will substitute. Initially, we have 3.3% of ethyl alcohol entering. We divide it by 0.78. And this is the expected maximum mole fraction of ethyl alcohol in the solvent that leaves your column already. So, this value, we will substitute in our equation 3 so that we will determine L prime minimum. So, 0 for XAO. These are the streams that we have determined already. This is your V prime. This is your YAN plus 1. This is your this is rather your XN maximum that we just solved. And this is your Y1 or YA1. You have this. Knowing the minimum will help you solve for the optimum solvent requirement, and we use 50% of the minimum value. So 50% of 77.28 will be 115.92 kilomole per hour. If you use this value of L prime of L optimum for the L prime minimum in the equation that we have here, we will solve for the actual Xn. This is the projected and this is the actual. So the actual is just 0.0286. The maximum projection is 0.0423. Knowing this as the actual, everything here you know already from the previous equation. We just copied the values. In here, we just change the L prime minimum to L optimum. L prime optimum to get the Xn, the actual Xn. So getting the actual Xn will help us find the Ln actual. The actual amount of solvent that leaves your column based on the actual mole fraction of ethyl alcohol that goes with it. Okay, so we have 119. So L prime optimum divided by this one will give you the actual Ln. So this is 119.33. That value of Ln and the other value 115.92, this one 115.59, and V sub n plus 1 will help you solve for the geometric mean, because if you notice, we have different values of the absorption factors here. We have this geometric mean, and we substitute the values in our Crimser equation. That gives us 4.02 as the actual number of stages. Specifically for this problem, that's the optimum number of stages. So again, we solve for all this. That way, we'll be able to find the geometric factors of the dilute and the concentrated ends of your column to see whether we need to go through finding the geometric mean. And the rest is just manner of substitution. So go through back the solution and get the values of your streams and substitute in the formula for Crimser equation. So for today, we have tackled, I think, 4 different ways wherein we can apply the principles of gas absorption initially for design problems later on, which we will be discussing next meeting. So we have learned how to determine solubility of the gas in the first sample problem. Then we have learned to determine the number of stages. Then we have learned how to determine the optimum number of stages based on the minimum solvent requirement. All of which are all preparatory for design problems in gas absorption and stripping. So if you have Any questions on this particular lecture slide on the first part of gas absorption and stripping? Feel free to drop me a line in the inbox of our Canvas course. You may also write me a message through my email or leave me a message in my messenger for things that you might want to be cleared with, or if you want some more discussion on some areas in this slide. So thank you. Hopefully I'm able to help you. Again, remember that this one is complementary to the comprehensive file or page in Canvas for the entirety of the topic of gas absorption and stripping. Have a good day, everyone.